Clarification through some of the work in electric potential. I've told you this, but I wanted to have it written down more explicitly. Work is change in energy. So that really gives us a new formula. Just taking the formula for change in electric energy is equal to work. Change in energy equals work. So taking this equation for potential difference, delta V is potential difference, we can say work equals to charge times potential difference. And this really leads us to the example that we did earlier. Just saying that if it takes that much work to move that much charge, find the potential difference. And so instead of using change in E, you just sub in W. It's the same thing, and you get your number 273. Okay, and that is a good. Volt numbers are typically in the range of regular numbers. I guess I would say, like the numbers we would scale from 0 to a couple thousand is typically the numbers we use. Okay, not millions usually. This is a killer example. But we're going to do it anyway. So these, imagine you have 3 charges, okay? And I know what the charges are. They're all, excuse me, microcoulombs. Okay, that's a negative down there, a positive and a positive. We know this is an equilateral triangle, so the distances here are all 2. And I want to find the total electric potential energy of the group of charges. And so remember, energy is not a vector, so there's no sign or necessary, or when I say sign, you know what I mean? There's no right or left or anything like that. Okay, it's just saying what's the total potential energy of this system. And to do that, it really is just, this looks like a lot, okay, but really I'm just saying, well, I guess that's the sum of electric energy between these two and these two and these two, right? And you just add it all up. I want to remind you that when dealing with energy, if it's a negative charge, you put the negative in here. This is going to be very difficult to keep straight in your mind. Forces you do not, energy you do. And that means that you can add or subtract from the potential, right, just based on the signs of the charges, and you get your number. So that's the total electric energy of that system. It's a joule, because just energy is just joules. Part B says determine the potential electric potential at the mid, like right down here. So this is saying I want to find electric potential is just V, not change in V, just V, and it's at this particular location. And actually, just looking here, so I'm saying V at point P. I'm calling it point P. I want to find the V. Then I guess I do need to know the distances. They're 2 meters long on each side. So that means that the distance from charge 2 to point P and charge 3 to point P is 1 meter. And here I have to use Pythagorean theorem to figure out this distance, where this is the hypotenuse, this is a meter, so this ends up being square root 3. Okay. So again, the potential at this location is the potential due to this one, plus the potential due to this one, potential due to this one. Again, keeping the signs in as they are. So, for example, Q1 is positive, so I keep it as positive. Notice R1P, I just put square root 3. I could have rounded that, but I'll just leave it as long as I can. 2 is a negative, so that's why this is negative. I didn't put the negative there, I just stuck it out front here. Okay? And you get an answer, and like I said, the answers are usually in the range of 0 to a few thousand volts, so that's not an unreasonable answer based on what I told you. And really, can we try to understand what it means? Well, what that's telling me is that 1 coulomb of charge located right here would have that much potential energy. And that means that if I put 1 coulomb of charge right here and it was free to move, and it would have the ability to gain that much kinetic energy if it was free to move. Okay? So, that's a little look at potential energy. That's it for potential. We're going to get into Millikan's oil drop experiment, which is a pretty cool thing, but you'll see.